Welcome to the demo session. So before we begin, let me start with my introduction. So I am Rahul. I have close to 9.5 years of experience in Teradata and Teradata's integration with other databases, Teradata's integration with big data and analytics. So I have built data warehouses, data platforms, and I have been part of numerous performance tuning projects as well. So in my current role, I manage a team and I am also the chief architect for the data analytics platform for a retail major. All right, so that's the background, and for the course, we will soon see all the topics that are there that we will cover. All right, so let's get started. Okay, so before I begin, let me first quickly give you a quick walkthrough of how the website looks like, right? So this is your course overview. Okay, so each module, so we'll have 8 modules, and within each module you will have a class recording. So this is available post the class. Okay, so today's introductory audio plus so today's introductory recording, the demo class, will be available to you. Okay, yes, just give me a second, guys. I am comfortable, okay, with in Unix and Linux, COBOL developer. Got it, got it. So there is a question that is the Teradata tool better than ETL, Informatica? Okay, so let me be um, unbiased and talk about it. Okay, so Informatica is the ETL tool, but then Teradata is something is actually a RDBMS. Okay, so I'm sure all of you have RDBMS knowledge, right? So Teradata is basically a database plus the ETL features are also enabled on top of it. So when you go and say create jobs in Informatica, what happens is you still need an underlying database. Teradata, on the other hand, has utilities like fastload, mload, TPT. So these are all scripting languages built on top of Teradata, which can be used to load and unload data into or out of the Teradata database. So I would say that Teradata is more complete when it comes to handling end-to-end data warehouses, but at the same time, it needs some amount of Unix and scripting knowledge, because Informatica is drag and drop, so it's easier for new users. But as you spend time in different systems, right, you would see that the more granular you go, the faster your systems are, right? So when it comes to the Teradata scripts, the way it helps is so what happens is when you do a connector from Informatica, internally it calls a TPT connection, a protocol, right? So rather than that, in Teradata, you will directly write that script. Okay, right? So I think that is my perspective, that Teradata is a more complete tool. Does that answer your question? All right. Okay. All right. So let us continue with looking at this website now. So for each module, you will have the class recording. You have the presentation. Then at the end of the class, you will have a quiz. You will have class file, which is basically the notes that I write throughout the class. I upload it here, right? And then you have an assignment, right? And then there is a pre-work for the next module. Okay, so once you log into your portal, once your ID gets created, you will have access to all of this, right? And this is lifetime. You will have access to it even after the class, and for this is a lifelong availability. Okay, next, for the curriculum, so these are the topics that we will be covering. So initially in module 1, we will be doing the overview, right? And the topics would be basic relational concepts. What is Teradata? Then how data is stored and retrieved, connectivity with mainframes and other network applications, and then what is UDA. After that, from module 2 onwards, it is more, so first module is basically a little bit of theory, but then from module 2 onwards, it's hands-on, right? So it's all about primary index, creating them, about primary key, their differences, what are the types of indexes that you can create in Teradata, right? So other indexes are join indexes, PPIs, partition primary index, and secondary index. So we will see when to use them, how to use them, right? If you have a job that is there not performing well, how do you leverage your indexes, right? And so from module 2 onwards, you will start getting uh, a good understanding, in-depth understanding of how Teradata works. Module 3 is about Teradata SQL, the basic SQL of create, alter, drop, the DML statements of insert, delete, and update. Then you have DCL, which is grant and revoke, data control language, right? So how do you do grant and revoke on different objects and control the access of your data? We'll also do order by, group by, and all of this will be hands-on, right? So we will write queries and see how to manipulate the data that is stored inside of Teradata, right? Next would be data protection. So Teradata is a MPP system. I will start with module 1's slide today in this class itself. So you would know how Teradata works and then what are the measures that makes it fault tolerant. Okay, it's a MPP system, which stands for massively parallel processing system, okay, which is a combination of a different SMPs, symmetric multiprocessing systems. A combination of that makes up a MPP. So we'll see what each of these are, right? And then how do you use transaction logs, what are fallback tables, and then how do you use all of these things to make sure that you never lose data, okay? And your system is always available. Even if your say data center goes down, some hardware fails, there is a network snag, you want to ensure that your business critical applications still run. So we'll see how to do that in data protection, which is module 4. Module 5 is for the business analysts or for the data analysts. It is about advanced SQL. How do you use them to look up data, use subqueries to fetch data, generate reports, right? So people who are using business objects, Tableau, all the reporting layers, right? So how do you write your queries to get data out, okay? And these are your complex queries. Once you have covered module 5, you will have a good understanding of what Teradata offers, and then in module 6, we will start with the different database objects, and then how do you do performance tuning of using these objects, right? And then module 7 and module 8 is about the ETL part of it, where we will touch upon the utilities, we will write sample scripts, and then we will load data onto a table, transform it, and then take the data out using these utilities. Okay, so that is a brief overview of what is there in each module, right? And once we dive into these modules and start writing our queries and start writing our scripts, this will all become clear. Okay, so that is the overview of the course. Now let us directly jump into the presentation. So getting started, right? So this is what is the objective. So I think everybody knows what is Teradata. For those who don't know, it's a massively parallel processing system, currently the market leader in the data warehousing space, right? And the best part is that it has a very robust optimizer. So internally, the systems that you will be using, the optimizer, the compiler, they are all very mature. There has been a lot of R&D that has research and development that has gone into it, and they are considered to be one of the best in the industry, right? So a lot of the job Like in Teradata, you really don't require hints. If I have to compare it with Oracle, you really don't require much of hints, right? So if you create your tables properly, you distribute them properly in a parallel system, right? The optimizer in Teradata is smart enough to run your queries with in the best way possible. Okay, so that gives Teradata some competitive advantage over other RDBMS, right? And then we will also look at the architecture. We'll start with it, but it's huge, so we will need a few more classes to complete that, but then we will start with the architecture today, and then how data is stored and retrieved in Teradata. Okay, all right. So as you can see here, it's the best analytical database, okay, which is scalable, and it follows all the ACID properties. So Teradata is atomic, it's consistent, it allows you to do isolation, and the data that is stored is durable. Okay, so it follows all the ACID properties of the RDBMS. Apart from that, the advantages of Teradata are it's linearly scalable. Okay, so if you add more hardware, your query and the capacity to store more data linearly increases. Similarly, if you reduce the number of users, your performance again improves. Okay, so it's linearly scalable. As you add a new node, when I say a node, it's similar to a laptop. So the moment I add it to the network, I improve upon the query's runtime because I have added some additional CPU, and then I also improve the the storage capacity because I have also added some hard disk, right? So, and that is measurable and that is linear in performance. Okay, it's parallelly efficient because what happens is you have multiple CPUs working in parallel. So if you consider, say, today's CPUs, which are, say, a quad core or an octa core processor, what happens is each of these processors work independently on a chunk of data. Okay, so if I have a big hard disk of, say, 1 terabyte and I have a quad core processor, and I can somehow tell my processor that you have 4 cores and one core is responsible for 1 to 250 GB, the next core is responsible for the data from 250 to 500 GB, the third core is responsible for 500 to 750 GB, and the last one is for the last block. If I can do something like that and then start doing operations, pushing data and reading out, right, it will be super fast. I'm using all my cores. So Teradata has successfully done that. Okay, so that's why all your cores, I mean, they are called AMPs in Teradata. They work in parallel and work only on the data they are responsible for. Okay, it is called as a, so this is because of something called as the shared nothing architecture. Okay, so neither the data nor the computation is shared across nodes. Okay, shared nothing. Next, the execution of complex queries with a maximum of 256 joins. Okay, so you can join multiple tables to get the result out of your system. Right, now a brief history. It started in 1976 at Caltech. 1984 it was the first enterprise-wide market launch, and then 92 it became the first data warehousing system that was launched at Walmart, and it has grown so far, okay, since then. Okay, and the number of customers has only increased over time. All right, so this is what we were talking about. It has large capacity, so if you have billions of rows in your table, you can still scale Teradata. Performance, it gives you like linearly performant system. By even if your data increases, you add a node, your performance again increases. Okay, so it is linearly scalable in terms of performance and capacity. Single version of truth because it supports multiple sessions, there is no data replication, so you keep data at one place and then you allow multiple sessions to read from the same data source. Therefore, what happens is, remember ACID, right? So it is always consistent, right? Manageable growth. This is what I was talking about. Additional nodes can be added without affecting performance, and it is fault tolerant. Module 4, data protection, we will see there are numerous ways in which Teradata has been made fault tolerant, both at the software level by doing uh, something called as replication fallbacks, and then also at the physical layer using like hardware standby nodes and all of that. Okay, so before I move ahead, are there any questions over what we have covered so far? Right, I will get to AMPs. AMPs are called access module processors. Okay, so I'll get to it in a few slides. The competitive advantage of Teradata: linear scalability, right? So adding nodes will increase the capacity and performance of the system. Unlimited parallelism, because it's designed to be parallel and shared nothing. So MPP systems, that is what they do, right? So let me draw a small diagram, I think, which will make things much easier. So say I have a disk here and I have another disk here, right? And then I have two processors here. So what happens is, if processor 2 reads data only from the disk 2, so this is called as a virtual disk or a V disk, okay, and this is also a V disk, and the processor, which is also called as a AMP, because the full name is access module processor. Okay, so these are your AMPs. So AMP1 reading data from V disk 1. Now what happens is, here, as you can see, nothing is shared, neither the data nor the computation of the processors. And finally, what you do is you merge them using something called as an enterprise system bus. In Teradata, it is called as the BINET. And then you send back this to the user. Okay. Now, does this diagram make sense? So do you guys agree that if I had one big chunk of memory and then all the processors, they were not segregated from each other, and they were all trying to read data. So say processor 1, instead of doing it parallelly, was trying to read all of the data in employee table, and then processor 2 picked up another task and was trying to read all of the data from, say, what should I say another big table called as transaction, right? So what would have happened is, because both of these tables are large tables, what would have finally happened is your RAM, which is basically shared memory, would be consumed, right? What would happen, basically what would have happened is, your employees select would be slow, and your transaction select will also be slow, because there is only one processor involved. The way Teradata handles this is by allocating two AMPs, which are two processors, to do this select, and tell transaction that, hey, just wait for a minute and I'll come back to you. Okay. In the production environment, anyways, that doesn't happen, because you do not have two processors, but you have multiple processors. So there is a empty processor which will anyways take this up, right? So there is one more module, we will look at it, which is called session management. So the session management is something that will take care of our problem of whether somebody gets allocated to take up the second query or not. Okay, session manager. Okay, so that is something that we will see in the next slide. But is this clear? So if you have two processors doing retrieving data for employee, and then you have another two processors retrieving data from transaction, the selects for on both these tables are much faster. Do we all agree to it? Guys, you will have to confirm at times. I ask these questions because I want to know that whether everyone is following this or not? Okay, all right, all right. Yogendra, is there a question? Clear with everyone. Nice. Okay, let me remove this drawing then. All right. So apart from that, it has a very mature optimizer, right, which has been fine-tuned throughout its history, and it can handle up to 64 joins in a query. It has very low CTO because all you have to do is to buy a Teradata server, call up the helpline number, field engineer comes, installs it, and you're ready to go. So that when you get the server, right, you get it with a user, which is called DBC, and then you also get it with a password, with a database, with a default database called as DBC. Like in MySQL, you have the test and the default, right? Similarly, Teradata comes with the DBC as its default database, okay, and the default user. So then what you do is you inherit everything from these users and from this database. So DBC is basically the entire size of your server, okay? So we will get in depth of all of this slowly, okay? As module 1 covers all of this, we'll get into all of that slowly. And then you also have load and unload utilities, okay, which are basically fast load. So here you have some traditional load utilities called as fast load, right, multi-load, mload, okay. Then you have BTEC, you have TPT, you have BTEC, you have Teradata Parallel Transporter, which is TPT. You have TPump, which is to stream data, okay. And you also have something called as fast export, FEXP, okay. So there are a lot of utilities. We'll be using all of them, right? And we will also see when to use which one, okay. All right. So the components and the architecture, let us get into it. So before I go here, let me get into this diagram and explain it from here. So what happens is that when you make a SQL request, right? So what I do here is, say I run a SQL request. So I do a select ID from, say, employee. Okay, that's a table. All right. So what happens is the moment I fire this query, so where do I fire this query? I have something called as Toad, right? Similar to a Toad, I have something called as SQL Assistant in Teradata. Okay, this is a client end tool. So like in a client server, right? You have a server running and then you have client applications that can basically push requests to your server, right? So SQL Assistant is one such client application, okay? So you run your select stars from here and then this gets submitted. So when this gets submitted, what do you think logically should be the first step? The first step should be to parse and check whether it is syntactically correct or not, right? So the first step here in the parser should be a syntax check, okay, which is exactly what happens here, syntax check, right? What is the next thing that happens? You will have to check whether the columns and the objects that you have mentioned, do they exist or not, right? So you'll also have to check objects, right? What is the third thing that you need to check? Third thing is the user who has requested for this data. Is the user authorized to look at that data or not? So you'll also have to do a privilege check, right? Privilege check. So these are the things that happen at this level, at the parser level, right? And then if there are some system tables, you'll have to replace data from the system tables and create a SQL token. Once you have created the SQL token, what happens is it goes to the optimizer. Now, what is the work of the optimizer? The optimizer based on, so what is the input to the optimizer? One is the SQL token from the parser, and another is metadata information from the system. Okay, metadata info from the system. Okay, now based on these these inputs, the optimizer will come up with different plans. Okay, different plans of how it is going to access the data. Teradata's optimizer is known as, okay, and this is highly important. Teradata's optimizer is a cost-based optimizer. Okay, it's a cost-based optimizer. So what happens here is that whichever plan, so I come up with plan 1, I come up with, say, this is plan number, okay, and this is the cost, corresponding cost for it. Okay, so what happens is, say plan number 1 is going to tell me that, okay, I'm going to do a full table scan, and to do the full table scan, so what is cost? Cost is basically time and CPU, right, and the resources and internal resources. So you add all of these up, that is your cost. So I'm going to take, say, 3 seconds to scan all the partitions, right? And I'm going to use some CPU cycles, which is, say, 4. And then the total cost for this step is 12, plus there is one more where it has to, if there is a where clause, I have to do a filter as well, which will take 2 seconds. It will need 1 CPU clock, so it is 2. So the total cost for plan 1 becomes 14. Okay. Similarly, there is another plan that comes up. The other plan says that I'm going to fetch data based on the index. So that's why I'm going to take only 2 seconds to fetch the data and only 1 CPU cycle, which is great. So first step is 2. Next step is to do the where clause. That is anyways on the entire data, so it is again 2 and 1. So it becomes 2. So the plan cost, so the cost of the second plan is just 4 units. So Teradata, having a cost-based optimizer, will pick up plan 2, and also it has something called as the visual explain. Okay, so the user will be able to see what plan has been finalized by the Teradata's optimizer. Okay, and that is the plan it will use to get the data out. No, so we can use, okay, there's a question that can we use Toad with Teradata, but the best way of using Teradata is to use the native application called as SQL Assistant or Teradata Studio Express. All right, this is the name, SQL Assistant or Teradata Studio, TD Studio software. Because what happens is Teradata connects to its system not using ANSI but using BTET, which is Teradata's way of connecting. Okay, it is called the Teradata mode, and it connects using that. And then the connectors are also 2. There is a normal JDBC connector, and then there is a .NET connector. So all of these are built in within these tools, okay, both Studio and SQL Assistant. So that's why I generally suggest that use SQL Assistant to run all your queries. Okay. All right. Okay. So if it was clear so far, then let us push the data onto the binet. So this layer called the message passing layer is called as the binet. Okay. It was with the US military. Okay, it came as a research project, and then it was given out to the open source world. So that's why the name is Banyan Network. The full form for Mainnet is actually Banyan Network. Okay, because that's how they named it. So Banyan Network. Okay, now what is this? So what happens is now your final SQL with the optimized plan. So this is basically a SQL which has been enriched with metadata. So this is with your metadata. This gets pushed onto your Binet. So this SQL token now has information about where should I go in which disk. So these are disks. So 1, disk 2, disk 3, and disk 4. So in these disks, the SQL with its metadata knows where the data lies. So it via this ESB, the Enterprise Serial Bus implementation, which is called as a Binet, it goes and hits the virtual processor, which is nothing but your AMP, okay, Access Module Processor. Now at this level, what do? You do a select from the data it is responsible for. So if I have 10,20 in disk 1, the processor, which is vproc1 AMP1, will only operate on 10,20. If I have 30, 40, and 50 in the other disks, AMP1, which is basically your processor, is not at all bothered to handle this data. Okay, so 30 AMP2 will be responsible for 30. Okay, nobody else is responsible. For AMP3, the only data it is responsible for is row number 40, and AMP4, the only rows it is responsible for is row number 50. Okay, ID equal to 50. Okay, so what has happened here? One select task has been broken down into 4 parts, with each processor handling its own data. Now, what if you were running a sum function? So AMP1 will run a sum function on 10 and 20 and give the value. Similarly, AMP2 will then add 30 to the sum that AMP1 has sent. AMP3 will have a local sum which it will add to this sum, and then AMP4 will finally add its own contribution. So here, as you can see, you have a local sum and then you have a global sum that happens when all the data has been retrieved from all the AMPs. Okay, so this step is in Teradata is called a merge. Okay, we'll see all of that when I run into the visual explain of it. Okay, so now is this clear what a AMP is and how it is fetching data and how the parallelism is basically happening here in the system? Are there any questions around this? Right, so there is a question that what happens if AMP1 fails to the local sum. So what happens is if you have fallback enabled, okay, so then so we will come to it. This is beyond the scope of this module, but for now just know that if the data is copied somewhere else, the other AMP basically takes over and gives out the result. So your table will still be available. Okay. There is one more question that does Teradata need special hardware or can it run on any hardware? So it can run on any hardware. Okay. So what happens is when you install it, it creates something called as, it creates its own file system, right? So like for anything, right? If you have Hadoop running, you will create a HDFS. If you have Linux running, it will create its own file system. Similarly, when Teradata runs, it creates its own FS, right? On top of which it starts operating. Okay. All right. Any more questions? Any follow-up questions? Okay, good to move ahead then. Can we move ahead to the next slide? All right, okay. All right, let me remove these drawings because, all right. So now let us look at what is the, now that we have seen the diagram, right? Let us come back to the slide and see what a node is. So I am saying that the node is a basic unit in the system and it consists of all of these softwares, right? So all of these modules. So it has a gateway. What is the gateway? The gateway is one that allowed me to run the select, right, in the diagram. Next, it went to a parsing engine where I did a syntax check, I prepared the query, prepared the execution plan, and then gave it to the AMPs. The AMPs are my processors, which are responsible for data management and conversion, and it also does the IO processing and the locking. Okay, so all of that has to be done by the processor, right? And once that is done, it then gives out the results back. All right, so this diagram is clear now. All right, so in the parsing engine, let us see what are the components. I have something called as a session manager. So the session manager is used to enable the user to do login. So someone has to be, so a software module has to be there to basically validate the user, right? The user logs in with his password. I need a software module to handle that. That module is called as session manager. As something called as the parser. What is the parser? The parser is going to check for syntax errors. It will check for the privileges and verify whether the column and the table exists or not. I have the optimizer, which optimizes the query and tells you that what is the best plan to run the query. And then the dispatcher, which basically pushes the SQL token enriched with metadata over the binet to the AMPs. Okay, all right. So what is the binet? Okay, the binet is actually a software and a hardware component. Okay, so when I say hardware, it has physical ESBs. Okay, so it has something like a physical ESB, okay, a pipe, a connector that connects two components. So if I have, say, a disk here, right, and I have a processor here, okay, so a USB can connect these two using hardware, actual hardware, okay, and also it is intelligent enough, so it also has a software module built on top of it, okay, so it has both of these components, and this provides networking capability to the Teradata database. Okay. Now, because it has a software component, it can support point-to-point, multicast, and broadcast communication. So based on the type of request that you are sending through the binet software decides whether to invoke a point-to-point communication. So if it knows that, okay, so think of this as a mailing system, right? So if I know that I have to send it to a particular address, I can directly send it to that address. But if then it is a promotional email that has to be, or it's a or it's any other information which has to be sent to 3 or 4 houses, then I'll possibly give it to 2 postmen, right? Who will go and deliver it to these different houses. So then it becomes a multicast, right? I have multiple messages to be delivered. And in a broadcast, I will simply deliver it to everyone because everyone needs to know it. Okay? So that's a broadcast. So a software module of the binet decides which protocol to involve for a particular data packet. Okay? Now, point to point, that's why as I have written here, is to a single amp, multicast is to multiple amps, and broadcast is to all the AMPs. All right, clear so far? Can we move on to the next slide? Okay, so these are AMPs, Access Module Processor. So AMPs are the database execution engine virtual processors within the system. What are they responsible for? Okay, so they're responsible for managing a portion of the database, managing a portion of each table. It does all the work associated with generating result set such as sorting as in if I do a order by column, then it is sorting. I can also do aggregation like average, max, min, sum. So it does aggregation. I can do join and I can do conversion as well. All of this is related to the data. So the access module processor, which is responsible for the data stored in its corresponding vDisk, virtual disk. So that's why AMP is responsible for all these operations. Okay. Apart from that, because I have to make it compliant and consistent, the data, so the data during changes, right? So during an update or during an insert, I have to acquire locks on top of the memory block or the table that is holding the data. So that's why AMP is also responsible for lock management. So when I'm trying to update, I should not have other records that will start reading from that same memory location. So I need to do a lock management as well. So AMPs do that. And then I have space management. So how much space to allocate, right? So all that is also there with the AMP. Okay. So now let us look at how a data is pushed onto the vDisk. So if I have a stream of data that is coming to me, okay, say the IDs which starts from 1 and ends at 11, right? What happens is if I run something like say insert into, okay, so what I'm doing here is say this is the employee table and these are my IDs, ID equals all of this, right? So if I keep doing inserts, so I do insert into EMP, right? Values, right? Values, and then I do 1. Next time I'll do value equal to 2, right? So if I keep doing that, what would happen is that all of these go through a specific algorithm called as the hash algorithm. Okay, so we will cover hashing in depth, but there is an algorithm called as hash algorithm where you pass this ID onto that algorithm. Okay, and this algorithm tells you the memory location. So this tells you the memory location where this record is supposed to land, where this record is supposed to be stored. Okay, so what happens is the moment I pass 1 and I pass that 1 through this algorithm, it tells that, hey, vdisk 1 is supposed to store it. So my 1 lands up here. When I pass 2, it says AMP2 should be responsible for this, and the vdisk corresponding to AMP2 is vdisk 2. So go and store it in vdisk 2. Then you have 3 stored, 4 stored, 5, 6, 7, 8, and 9. Okay, so the hashing algorithm decides where each of these records should lie. Okay, so that's the storage part of it. Now what happens when I want to when I want to select this data? Okay, so when I'm running a select on top of it. So let's see what happens. So so this is data storage, which we have already covered. This is the retrieval part of it. So once your data is lying in the AMPs, if I run a select star on the table, star from EMP, right? If I run I'm not using the notepad today, but yeah, from the next class, let's start using that, because I'm also drawing all of this to explain the diagram. So that's why I'm writing it here. Okay, but we will use the notepad from the next class. Just pardon my bad handwriting. Okay, all right. So what happens here is that, look at this, there is no where clause. So I need to get all the data out. So what is the kind of protocol that gets invoked here from the BINET? The protocol is a broadcast protocol, right? It's a broadcast protocol, correct? So I go out to all the AMPs and say, hey, give me back the data that you're responsible for. So this one gives me 1 and 5. This one gives me all these three, all these three, and all these three. So these are finally over the BINET, they are merged, and I send that out to the user over here. Okay, so that's how your select is working. Okay, before I go to the next slide, was this clear? Insertion, I'm sure you would have understood. Now you also understood this, how once the data is inserted and staying in a distributed fashion across all the disks, you also understand how the select is going to work, right? Your select will also be distributed because my data is in 4 different disks which are attached to 4 different processors, and then these processors are operating on the data they are responsible for, right? So finally they're merged together, sent it out to the user. Is this clear? Okay, all right. No, because what happens is, if you don't tell me, I will not know if you have any questions, and then, okay, all right. Okay, so now let us look at the next slide. Okay, so all of these disks, which are called as V disks, right? What happens is that they store all of the tables uniformly. Okay, so if I have 10 tables in a database, each table will have a footprint on each of the V disk. Okay, when I say each table will have a footprint on the V disk is, say if you have only one record here, think of it from that you have to go to that depth and think, right? If I have just one record, then I cannot have that in all the 4 disks, right? What will happen is the record, say for customer row 1, customer record 1 gets stored in this AMP. All of these will have a header saying that customer record, customer table is present. But then, so there is an instance of this, but there is no data inside it. Okay, so there is so tables, you can think of tables as containers of data. So you can have an empty container with no data in it, or you can have a container with data in it. But that container will be there on all your AMPs. And sorry, not on all your AMPs, that will be there on all your VDisks. AMPs are responsible for the VDisks. So at times, I mean, as we move forward, people will say AMPs. Okay, the moment they say AMPs, you will have to think in your mind, okay, that's a processor that has a VDisk attached to it, and that's an AMP. Okay, you will have to think like that. Okay, so what happens is these containers are all instantiated across all the AMPs, but not all of them have data. If you have number of rows is less than the number of AMPs, you cannot have the same row in all AMPs, right? You just have one place, single version of truth. Correct? Clear with this? Similarly for the product table also. You have instances of product table and all the AMPs. Clear with this? Okay. Question. What is the use of empty container? Let me tell you that it is just for your understanding. Okay, I do not say empty container. What happens is the moment you write, say, a employee table, okay, you do a create table, employee ID integer, and create it, execute it. What happens is your EMP table also gets a instance here. So EMP. But if I run a query to see if there is any data in the EMP, I have not stored any data, right? So even though this EMP table has been instantiated, which means that it has been created, and the metadata tables, the system tables, they know that there is a table called as EMP. Otherwise, if you run a select on an empty table, it would have given you an error, right? If the table is not created, right? So you can have empty tables. There is no constraint on that, right? But once you start pushing data, right, that's when these containers get filled up. Okay, that is all I wanted to mention. It is like making a reservation in a good restaurant, right? But then to enjoy the food, you have to turn up, right? Something like that. Okay, so it's a container saying that, hey, I'm coming, but then I have not arrived yet, right? The data is not there yet, right? Or in a meeting, I have accepted the invite saying that, hey, I'm there, okay? But then have I attended the meeting or not, right? So it is something like that. It's a token that says that there is a table called as EMP, and the moment data starts coming in, it is going to stay here, marked to this container. Okay. So this is just to make you understand the parallelism of the entire system. So even when you create the table, you have these instances on each AMP. Okay. Now, was that clear? All right. So, okay. So hands-on, we will do it from the next class. Okay. Because we will have to set up the system, and then we will do the hands-on, right? But from the course point of view, are there any questions with the architecture that we have covered so far? Any questions here over the slides that we have covered today? Are there any questions? Okay, so let me do one thing. Let me unmute you one by one and take up the questions. Okay, so Raj, you're first. Just give me a moment. Hey, Rajendra?
Yeah, Rahul. So
Yes.
my question is the AMP, when you're creating the AMP, is it something that like we create in virtual VC using VMware? How is the partitioning? How it is done actually? Is it some that does the binding basically processor to disk binding?
Similar. Yes, 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 yes.
Yeah, one is that question. Another
Mhm.
thing question is like if you have a multi-node, so the top layer what you have said, where is the parsing and this thing done? Is it something they request from the client, how it comes to some load balance or something, or how it is done?
I did not understand this question. Can you repeat that?
Like from like let's say you have a 4 node system, the
Correct.
data is
Right.
partitioned across 4 systems.
Hmm.
So the client, the request will be landing to some point from where it will be distributed
That
across
is correct.
4.
Yes. Yes.
So that is the something in between some some load balancer something comes into picture, or how it is done?
No, I will answer both of them. So first is
Okay.
load balancer. The second one is about the
First one is
virtualization, right?
AMP.
AMP.
Yeah, how they have AMP. Yeah,
How
AMP
is
to
it
this
tied to the
processing
physical
and this
layer?
binding happens.
Got it. Got it. Very good questions, Rajendra. Okay. I
Okay.
let me explain them. Yeah. So let me go back to the diagram here. Let us go here. Okay. So what happens here is that you can have So let me first draw something like this. If I have a laptop, okay.
Yeah.
So if I say have a laptop here and I have another laptop here, right?
Yeah.
So just two nodes, for example,
Yeah.
okay. Now what happens here is that these are say connected using a physical layer, which I can say
Yeah.
is the binet,
Right.
okay. Now what happens here is that both of them have a component called as parsing engine, okay,
Okay.
PE, which is this component, okay. This
Yeah.
is your PE or the parsing engine.
Mhm.
So the parsing engine is responsible for your session management. So what happens is node 1, which is, okay, let me say N1 and N2. So if I have these two, so what can happen is this software module, which is PE1, can handle up to 120 sessions or 120 connections. So I fire my first SQL, okay. It is responded from this parsing engine and this one takes it up, okay. Similarly, I have another, so once this 120 is over, what happens is this parsing engine takes over, okay. And this can also service up to 120 sessions in parallel. So your next SQL, the 121st SQL, will be serviced from this parsing engine. So both of these nodes are capable of doing it, okay. And both of them can submit their request to the, so they will basically do a parsing, which is syntax check. They will submit it to the optimizer, get the data out, and then finally get a final SQL token out enriched with metadata, okay. This is internal, okay.
Okay. Okay.
This is clear so far?
Yeah, a little bit actually that when you draw the laptop, is it something the node, the Teradata node or what? And let's say I'm just comparing that this way. Suppose I'm connected from my laptop. I'm firing some query. Okay, send me the some like monthly sale something. Let's say, and
Hmm,
my table is split it across 4 nodes.
that's right.
Right. So in that case, the my client is single. From laptop, I am some connected to using some
Right. So
client, let's say SQL.
I drew this right. There is a SQL,
Yeah.
yeah, you were
Correct.
right. So there is a
Yeah.
SQL Assistant app, right? An
Right.
application that makes this request. So what
Yeah.
has
It
to
will be going
happen
to one
is
IP some.
correct. And then let me
Yeah.
change the pen color so it will be easier. Okay. And then what happens is this thing is your server,
Yeah.
right? This thing is your server. So
Okay. Yeah.
yeah. And on the server, you need to have a software module that listens to incoming connections, correct?
Right. Listen.
So
Yeah. Correct.
pooling, right?
Yeah.
That is what you will do. So you will have
Yeah.
to listen to incoming connections. So your incoming
Yeah.
connection is from your SQL Assistant. So the
Yeah.
parsing engine has a module that called as the session manager that listens to it and then
Yeah.
assigns a pipe. So whenever you
Yeah.
push request, right, you are basically getting a dedicated pipe using which you can. So once you do a log on, right, you do not, unless you don't do a log off, this will open. This will remain open, this
Yeah.
connection, right?
Yeah.
Correct? And you keep pushing your
Yeah.
request through
That's
this
correct.
pipe,
Mm. Yeah.
right? This is correct. This is
Yeah.
this is clear. Now what happens
Right.
is when this SQL reaches your optimizer, that's when
Yeah.
your explain plan or your
Yeah.
optimized plan gets generated. That's the load balancing part that you are talking about, right? That how
No.
do I
Yeah.
get the
My
data?
question. Yeah. My question little different. Like let's say I have a 4 system. Each system has 4 hard disks, and each system has let's say 2 node. Like let's say 4 processors. So
Okay,
the first thing is that is like the single node. That concept is very clear. It will some port will be listening the request and it will do the
correct.
generate the plan and send the request for same system. But if there are four physical system,
Okay. Okay. Right.
in
So
that case,
these, right. So these systems, see, these systems, they are not, uh, so these are connected, right? What will happen is
yeah,
these systems are connected via a pipe,
yeah.
right? They have
But
to be
where the
connected.
request of first request, the request from client side will go to one IP somewhere,
Right.
right?
Any one of these nodes take up. So
Okay.
I am not sure if you have experience with, like, if you have Cassandra or if masterless systems, right? Any of them
Yeah,
first
yeah.
service the request. Once it knows that this is a request
Okay,
that I have
okay,
to
I got it.
service to, then it tells all the
Yeah,
other
I got it.
neighbors that, hey, there is a request, and whoever has the data, just start giving it. Okay, so that
Yeah,
is
I
what
got it. I
the
got it.
optimizer does. Clear
Yeah, I
now?
got that.
Okay,
Yeah,
okay.
any one of the node it will get the request and it
Yes,
respond to other nodes actually. Look it based on that data where data lying, it will distribute the request to the
right,
other nodes.
right, right.
Yeah.
Absolutely. Okay. What was the
Okay. Yeah.
second
Thank
question?
you.
There was one more question.
Second question was the mapping between app and the physical disk. Is there something
Correct.
some like where we map basically the okay this processor this table or this disk
It's
something
a
like that?
configuration. Yes, absolutely. You are correct. It's a configuration. So say if I
Okay.
have, uh, so what will happen is if I have a processor here, right? So what will happen is,
Yeah.
okay, let me draw it in this diagram itself. So say
Yeah.
I have this block here,
Yeah.
okay? And this block is currently using at the, okay, and let me draw the physical layer using any other color, blue. Okay. And in the physical layer, I have a actual processor and I have
Yeah.
a actual physical array,
Disk. Yes.
correct? So
Yeah.
now what happens is this is called as a vdisk. Okay.
Yeah.
This part is
Yeah.
called as a vdisk or a virtual disk.
Yeah.
Okay. And this is your physical layer. So this is your physical array. Okay. Now what
Yeah.
happens is if there is a failure in the physical array, but your CPU is still running, right? Your physical CPU is still running. So basically this AMP is still running,
Yeah.
correct? Now, if this disk is not available, if I have virtualization built on top of my physical layer, what happens is, say this config gave a number, say 101, okay, which is basically the place in the disk for which it was responsible for, correct? If I know that there is one more physical array that starts at 301 where my data is replicated. So we'll see all of that in module 4. So if I know that from 301, the same data has been replicated, fallback copy, okay? So this vdisk, only with a change of config, it can start pointing to this physical array, right?
Yeah. Yeah.
So there is no need of any I mean, I really don't need to
Yeah.
do a server restart or something. All I do is, so this is a hot swap, right? I change the config and my data becomes available again.
So this replication is happening at the RAID, like the physical hard RAID level, or it is a software RAID kind of
At
thing?
both the level, yes. In the physical level, I have RAID 1, which is mirroring, and RAID S,
Okay.
okay, which
Okay.
is the parity bit at the physical level.
Okay.
So at this level.
Okay.
And
Okay.
then in the software level, what I do is
Okay.
the copy of vdisk here, say if I have 10, which is the ID,
Yeah.
I will have a copy of 10 in another vdisk itself.
Okay. So that will
Okay.
be configurable how many copy will be needed, how
A
many
fallback
replication.
is always 2, unlike Hadoop
Is it
or
fixed?
unlike the NoSQL systems like Cassandra, where you set the quorum, or you can have, I mean, basically you can have a replication factor, right? RF equal to, you set that.
Yeah.
Here it is
Even
2.
Vertica also has the same thing.
Yes, yes, yes. But here the fallback is 2.
Okay. It's a fixed. Okay.
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 Right.
Yeah, that's clear.
Okay. Any other question? Any follow-up questions?
Yeah, thank you. The
All right.
question is
Okay.
really many, but like,
All right. Okay. All right.
yeah, thank
Anyone
you.
else? No problem. No problem. All right. And anyone else? Any more questions? Okay. All right. So let's do this. So if there are no more questions, let me remove the drawing. Let's see if we have something remaining. Right. So if there are no more questions, then let us wrap up. Okay. And thank you for being a wonderful audience. Right. So I hope to see you in the next class. There is a, so this is, okay, this is a marketing slide. Okay. So I really don't like this, but yeah, if you want to join us, there is flat 15% off that's going on currently. Okay, you just have to log on to the portal, and there is a career booster as well that's going on. Okay, so let's meet in module 1. Okay, I hope to see you in the batch, and thank you again for joining in. Have a uh, good day or a good evening for people in Asia, and a good day for my uh, for people who have joined in from the US and the Canada. Okay, so thank you so much, and I look forward to talking to you once again. Okay, thanks for now.